Hello, good morning, my dear students. This is again your Virat Kumar, a lecturer in Electrical and Electronics Engineering from the Institute of Power and Polytechnic, Vadipalli, with the same semester of 4, the subject of AC machines with the code of 18EE403C from the topic of single phase transformers. Here we are to deal with all day efficiency of the single phase transformer. The topic is all day efficiency of a single phase transformer. What does all day efficiency mean? Since the transformer works continuously for 24/7, but the efficiency varies from time to time because the load on the transformer will vary according to time, because during night the load will be very light, and during daytime or else in the evening the load will be very high. So due to these changes the efficiency varies. So we'll be seeing the overall efficiency of a transformer. And in the previous class we have learnt about voltage regulation and efficiency, and also some problems on it, and also we have seen maximum efficiency, it is efficiently. And now the topic is to know the importance of all day efficiency and determine the all day efficiency of a transformer for a given load cycle. So here there will be some load cycles from the mid 12 to again to the 12. How the variation of the load, there will be a load cycle given to us. For that we need to calculate the all day efficiency. Okay, no problem, we can analyze the given data from the so the given data here is the kVA of the transformer is equal to 200, the 60 kW at 0.8 power factor, and the kVA is 160 by 0.8, that gives us 200, and 80 kilowatts at unity power factor, and the kVA for that is 80 by 1, that gives us 80, and the no load kVA is equal to 0 by 10, that is equal to 0. The full load copper losses is 3.02 kilowatts and the iron losses of 1.6 kilowatts. Yes, please make a note of this. So finally there is a kVA of the transformer is 200, and at 60 kW at 0.8 power factor the kVA is 200, and 80 kW at unity power factor the kVA is 80, and at no load kVA it is 0, and full load copper losses and iron losses are 3.02 kW and 1.6 kilowatts. Now the required data is all day efficiency of a transformer. Required data is all day efficiency of a transformer. Now the solution, we know that the all day efficiency of a transformer is given by the same. We know that the efficiency is output by input as usually, but whereas the all day efficiency is given as like output energy in a 24 hours by input energy in a 24 hours. Output energy in a 24 hours by input energy in a 24 hours. Just please make a note of this formula. The all day efficiency. It is nothing but output energy in a 24 hours by input energy in a 24 hours. Output energy in 24 hours. This should be noted. Same input energy in 24 hours. Now going on to the problem, you can see here output energy in a 24 hours is equals to 160 into 8 plus 80 into 6 plus 0 into 10. What is this? 8, 6 and 10 is, this is 8 hours, 6 and 10. You can see that 8 plus 6 plus 10 gets 24. So for 8 hours the load being 160 kW, and for 6 hours, for next 6 hours the load being 80 watts, and for next 10 hours there is no load. That may be during night. So now the total load in kWh, when you just multiply kW with time, nothing but the hour, it gets kWh. So this will be the total output energy in 24 hours. The total is 1760 kilowatts. Now total copper losses for 24 hours. Similarly, it is 3.02 into 8 plus 80 by 200 square. This is actually this is the full load copper loss, and this is time. For particular time, it should be added to the actual kVA by full load kVA. That means the full load, the time respective to the time, full load kVA by actual kVA whole square. So for this particular time it is 80 by 200 whole square into 3.02 plus 0 into 10. That gets the total of 27.059 kilowatt hour. Now the iron losses for 24 hours will be directly multiplied into 24, since there is no variation in the iron loss. So directly 1.6 into 24, that gets 38.4 kW. Now total energy loss is equal to copper loss plus iron loss, that is 27.059 plus 38.4 gets 65.459 kWh. Now the energy input in 24 hours is equals to output plus losses. We have output of 1760 kWh and out losses of 65.459, and the total of 1825.459 kWh. Now we have total output in 24 hours and the total input in 24 hours. So now we can easily calculate the efficiency, all day efficiency, nothing but output in 24 hours by input in 24 hours. You can see here all day efficiency is equal to output energy in 24 hours by input energy in 24 hours. We have output energies for 1760 divided by input energies for 1825.459. That gets 0.9641, and if it is for percentage into 100, that gets 96.41%. Please make a note of that. Okay, move on to the next problem. Problem number 2. A transformer has a maximum efficiency of 98%. A transformer has a maximum efficiency of 98% at 15 kVA at UPF. And during a day, it is loaded as following. You can see previously we have just missed out the question. We have directly moved with the given data and required data in the answer. But you just see carefully. We have a question over here. For 10 hours of duration, the load is of for 10 hours of duration, the load is of 3 kW at 0.6 power factor. For the first 10 hours of duration, the load is of 3 kilowatts at 0.6 power factor. And for next 5 hours of duration, the load is of 10 kilowatts at 0.8 power factor. And for next 5 hours of duration, the load is of 18 kilowatts at 0.9 power factor. And for the next 4 hours of duration, there is no load. So you can total add the duration 10 plus 5 15 520 and 4 24 hours. So total 24 hours. So for the 24 hours he just gave you the load details. For the 10 hours it is 3 kW at 0.6 power factor, and for 5 hours it is 10 kW at 0.8 power factor, and for 5 hours it is 18 kW at 0.9 power factor, and for 4 hours it is for no load. Now moving to the problem. Calculate the all day efficiency of a transformer. Now the given data is, see, 3 kilowatts at 0.6 power factor for 10 hours. So here the kVA is 3 by nothing but kW by power factor gets the kVA. So simply in order to find a kVA, we need to do kW by power factor. So it's 3 kW and power factor is 0.6. So 3 by 0.6 gets 5. So kVA is 5. That means we need to convert this kW value into kVA. So for 10 kW with 0.8 power factor of 5 hours duration, and the kVA is 10 by 0.8 simply. So here first it is 5 kVA, here it is 12.5 kVA. For 18 kW, 8.9 power factor with 5 hours, the kVA is 20, simply 18 by 0.9. For no load of for 4 hours, since there is no load, it is 0 by 0 is 0. There is no power factor and no time or something, so 0. The kVA here is 0. And we have the maximum efficiency of 98%. The load at which maximum efficiency occurs is 15 kVA at unity power factor. The load at which maximum efficiency occurs is equals to 15 kVA at unity power factor. The required data is all day efficiency. The formula for all day efficiency is already known, like output energy in 24 hours by input energy in 24 hours. By input energy in 24 hours. So here the all day efficiency is of output energy in 24 hours by input energy in 24 hours. Now we'll see the solution. So at maximum efficiency, he just given us the maximum efficiency condition. The reason is that we need to understand that the iron losses and copper losses are same. See here, the copper losses and iron losses are same. So for the output is equal to kVA into cos pi. Since the load kVA at maximum efficiency is 15 kVA with unity power factor, so kVA into cos pi gets the kW. So 15 into 1 gets 15 kW. Now the input is equals to output plus iron losses plus copper loss. We have the input of 15 kW. Since the iron loss and copper loss is same at maximum efficiency, so it is double the losses 2 Pc. So 15 plus 2 Pc. Since Pc is equals to Pi, nothing but Pc is copper loss, Pi is iron loss. Both are same, so it is 2 Pc. So the input is equals to 15 plus 2 Pc. Now we have the efficiency equals to output by input. The maximum efficiency is 0.98 and the output is 15. The input is 15 plus 2 Pc. So by solving this, we get PC is equal to 0.153 kW. This copper loss at 15 kVA is equals to 0.153 kilowatts. The iron losses are also same, 0.153 kW. The copper losses at 15 kVA is 0.153 kW and the iron losses are also same. So now for output energy in a 24 hours is equals to kW into time, 3 into 10, 10 into 5, 18 into 5. There is no load for 4 hours, 0 into 4. 3 into 10, 30, 10 into 5, 50, 18 into 5, 90, 0 into 4 is 0. So 30 plus 50 is 80 and 90, 170 kWh. And the total copper losses for a 24 hours is equals to 0.153 into 5 by 15 square, the actual kVA by full load kVA. That is 5 by 15 square plus 0.153 into, for the second load is 12.5 by 15 is 5 by 15 square, and for the second load it is 12 by 5, 12.5 by 15 square. For third load it is 20 by 15 of square, and for second and for last it is 0. 0 by anything of square is 0. So 0 into 1.53 is also 0. So by solving all these things, we will be getting the total copper loss for 24 hours is 2.06 kWh. Now finding the total iron loss for 24 hours is directly multiplying by 0.153 into 24 gets 3.672 kWh, and we have output for in kWh and the losses in kWh for copper and iron. Now we need to find input. So the total energy losses is equal to copper loss plus iron loss. The copper loss is 2.06 and iron loss is 3.672, and this has a total of 5.732 kWh. Now the energy input for 24 hours is equals to output plus total losses. Output in kWh is 170 and total losses in kWh is 5.732. That gets in a total of 175.732 kWh. Just please make a note of this. And we have output in kWh and input in kWh in our hands. By that we can easily calculate the all day efficiency of a transformer. If it is done with this, please calculate the all day efficiency. You can cross check the answer, which is over here. Output energy in 24 hours by input energy in 24 hours. The output energy in 24 hours is 170 and the input energy is 175.732. That gives 0.9674. If it is multiplied with 100, we'll be getting percentage efficiency, that is 96.74%. Please make a note of this. And at maximum efficiency, iron losses and copper losses are equal. So output in kW is 100 into 100 kW. Input is equal to output plus losses, 100 plus losses. The maximum efficiency is output by input. One second. You can just see the similar question. Now we have maximum efficiency. He's telling us that maximum efficiency, and we have the condition iron loss is equal to copper loss. Output in kW is equal to 100 into 100 kW. The input is equal to output plus losses, 100 plus losses. So we have the maximum efficiency out of input. Output is 100 and input is 100 plus losses. The maximum efficiency of 0.98. By solving this, we will be getting losses. So the total losses is equals to 102 minus 100 is equal to 2 kW. So these 2 kilowatts are in a total of Wi and Wc. So at maximum efficiency, the copper loss is equal to iron loss, that is equal to total loss by 2. That means 2 by 2 is equal to 1 kW each. So iron loss is also 1 kilowatt and copper loss is also 1 kilowatt. And for 12 hours of duration, the energy output is 20 into 12, it's 240 kWh. The kVA is equals to 20 by 0.5, it's 40 kVA. So copper loss for 12 hours is equals to 40 kVA by full load kVA whole square into 1 into 12. That gets you 1.92 kWh. This is not into 2, this is square. This is square. One is copper loss for full load and for 12 hours is H, and this is for copper loss at 12 hours. That should be actual kVA by full load kVA whole square into copper loss into time. And for 6 hours the energy output is 45 into 6, 270 kilowatt hours. And kVA is equal to 45 by 0.9, that gets you 50 kVA. And the copper loss for this 6 hours is 50 kVA is present kVA for this actual kVA by full load kVA whole square, this is square, into 1 into 6 gets you 1.50 kilowatt hours. And for last 6 hours the energy output is 80 into 6, it's 480 kilowatt hours, and for kVA load is 80 by 0.8, it's 100 kVA, which is nothing but the full load. If copper loss for 6 hours is actually 100 by 100 whole square becomes 1, so 1 into 1 is 1 and 1 into 6 again 6 kWh. Therefore the total copper losses is for all the durations and all the loads, first one 1.92, 1.5 and 6, in a total of 9.42 kilowatt hours. Therefore the total copper loss is of 9.42 kilowatt hours. The total iron loss is simply multiplied the iron loss kW into time into 24. So 1 into 24 gets 24 kWh. The total energy loss is equals to, this is the copper loss and this is the iron loss, in a total of 33.42 kilowatt hours. Now the total energy output is equals to 240 for the first duration, 270 for second, and 480 for last, and in a total of 990 kilowatt hours. Now we have output in kWh and the losses in kWh. We will be finding simply the input is equals to the total energy input is equals to energy output by energy output plus energy losses. Energy output is equals to 990 plus 33.42 is equals to 1023.42 kilowatt hours. So now we have the total energy input and output. Now we can find the all day efficiency with the total energy output in 24 hours by the total energy input for 24 hours. That is 990 by 1023.42 into 100. That's the percentage all day efficiency. That is 96.73%. Please make a note of that. Please make a note of this. Make it quickly. If it is done, we'll move on to the next. Next, you can see the kVA of a transformer is 100 kVA. The maximum efficiency is 98% at UPF, and to find all day efficiency of a transformer. The formula for all day efficiency is total energy output for 24 hours by total energy input for 24 hours. So this is also, there is no question for that. The question was missing. So these are the given data to find all day efficiency. And the respective loads has to be given for this. So there was some loads are missing. You can take the loads of the previous problem and try to solve this problem. And for the today's summary is, in this class we have discussed about the all day efficiency is the ratio of energy output in a 24 hours to energy input during the same 24 hours. And the all day efficiency is used to judge the performance of a distribution transformer. Now please make a note of all these things. The all day efficiency is less than the commercial efficiency. These are all important bits. Determination of all day efficiency of a transformer. for a given load cycle is done. So it is of all day efficiency is the ratio of energy output in 24 hours to the energy input during the same 24 hours. The all day efficiency is used to judge the performance of distribution transformer, not for power transformers. And the all day efficiency is less than the commercial efficiency. All day efficiency is less than the commercial efficiency. Determination of all day efficiency of a transformer for a given load cycle is determined. We have determined. These two are main important bits for reset point of view and also for competitive point of view. There are also some more problems, like frequently asked questions are define all day efficiency. There are some problems like a 20 kVA transformer has a maximum efficiency of 98% when delivering 3/4 full load at unity power factor. If during a day it is loaded as following, calculate the all day efficiency. No load for 24 hours and 12 kilowatts at 0.8 power factor for 6 hours. 20 kW at unity power factor for 6 hours. And there is the answer also for this. You can solve the problem and cross check the answer. There is the other question also to you. Just read it out and try to solve the problem and cross check the answer. See the question, the total losses at full load in a 100 kVA distribution transformer, amount of kW is 3, during a day loaded as follows. full load for 3 hours, half load for 4 hours, no load for 17 hours. If the losses are equally divided at full load, calculate the all day efficiency assuming all the load is lighting load. There is a small quiz. The performance of a distribution transformer is judged on commercial efficiency, all day efficiency, both A and B. The performance of a distribution transformer is judged by all day efficiency and also by commercial efficiencies. So it is for both A and B. All day efficiency is always dash than commercial efficiency. Less than, greater than, equal, none of the above. Less than, previously we have seen in the summary. Less than. All day efficiency is defined on the basis of power, energy, voltage, current. Energy. It's energy.